In this video we're going to cover the AQA specification for AS and A-level integration. There are 8 parts and I'll just label them just so you know. The first one we're going to do is H1. If you do want to see any other specification, be sure to comment that below so I know. But for now, let's just get into this video. So H1 is the fundamental theorem of calculus, and this is essentially intuitive, but it's good to know formally. And that's if you take the derivative of respect to x, of a function f of t integrated with respect to t, then that is equal to f of x, and that is essentially it. Yeah, as I say, not much to it to that, but there is a second part to the theorem. That is, this is the one you need to know a little bit more commonly. If you take the limits here, a function f of x with respect to x, then this is equal to f of a. And this capital F represents, the integral of this f of x function. So say f of x was x squared. Big F of x would be, well, 1/3 x cubed, alright? So that's what you need to know for the fundamental theorem of calculus at this level, and I'll get on to the next part. Right, so H2 is some common integration results. So this will be 1 over n plus 1, xn plus 1, and when integrating indefinitely, we call this, so with no limit, you have to put a constant of integration on the end, because you can imagine if I had plus 7 here and I differentiate it to get this, like the 7 would just disappear, so you have to add that constant on. E to the x just differentiates to e to the x, integrates to e to the x, but it does also differentiate to e to the x. This is another common result, just goes to ln x. So you can see the pattern here, all these are just the opposite of the differentiation going the other way, so from here to here, well, this is the inverse. So this now, well, sine kx goes to k cos kx, so what we'll do is we'll go minus 1 over k, and still remember plus c, and then this one is equal to minus 1 over k, not minus, sorry, this is just 1 over k, sine kx plus c, and the way we remember this is we can sin x cos x minus sine x minus cos x, and this way is the differentials, so clockwise to differentiate, and then anti-clockwise on the integrals. Alright, so that's it for H2. The only other thing to add is, it says here you should be able to integrate related sums, differences, and constant. For all of these, if we'll take the thing of the constant multiple, you can just take any constant multiples out. So say we have the integral of a e to the x with respect to x, that is equal to a multiplied by the integral of e to the x with respect to x. So this will be equal to, if we take this, either a e to the x plus c, or we can just call ac a different constant, so we'd have a e to the x plus d, right? When it comes to sums and differences, if you got functions added together in the integral, you can just integrate these independently and then add them together. So what I'm saying there is you got integral of f of x plus g of x with respect to x. This is equal to the integral for f of x with respect to x plus the integral of g of x with respect to x. So that's it for H2. The next section that you're supposed to understand is understanding that integration can be used to evaluate areas, and you should be able to evaluate definite integrals. But essentially, say we got this graph and this is the function f of x. That area I is equal to the integral from b to a of f of x with respect to x. And you can remember from the first time how we calculate this. The only other thing in H3, I'll just do a quick freehand sketch. If we've got, for example, let's say a function f of x. That's just ignore the terrible drawing that I know. But this f of x can just function, but it's just in this case just a constant function. But this is just a drawing, so it wouldn't always be. And then we've got g of x function, and we want to find this area here. Okay. Well, all we can do is, knowing these rules, we can find the under f of x between a and b. So that would be this formula here. Be a f of x dx, but we don't want to include this area, and this function is g of x. I'll just call it that, but you can call it whatever. So we want to subtract this area, and this area would be the integral from b to a of g of x with respect to x. So H3 is a pretty simple conceptually, but sometimes the functions aren't as clear cut as this, and it might be a bit more difficult to find an area. So I suggest doing lots of practice questions, and there will be more in-depth videos on all these topics in this video, so stay tuned for that. For H4, I'm not going to go too far into this. I'll explain a little bit more in another video. This is a terrible diagram. The point is, so why does integration work? Well, if you take little strips and work out the individual areas, as you can see, we've got a sum here. It's this section plus this plus this plus this plus this. As you formulate this and make these segments almost infinitesimally close to each other, you get the integration result, and we'll go through this later on. But for now, if you can just understand conceptually, that'll do. So the next thing, HI, is integration by substitution and integration by parts, and the specification also says it wants students to understand that these are the opposite of the chain rule and the product rule. So if we want to integrate something like this with respect to x, so we've got a function f on a function g of x multiplied by the derivative of g of x. Well, this makes sense because we use, to get to this position, we would have been differentiating a function within a function and then multiplying by that the derivative of that function within the function. So now we're looking at what we have to do to reverse this. It's a little bit tougher as you have to guess the function, but essentially what you do is you get, if you have u equal to g of x, then du by dx is equal to g dash of x. So then dx is equal to du over g dash of x. Okay? And then you substitute that in, and the u is equal to g of x, so this just leads to this whole integral being equal to f of u with respect to u. As you see, if you substitute dx in, you get du over g dash of x, those cancel each other out, this g of x just becomes u, so this is much easier to integrate if you select your function right. So as I say, in future videos we'll do lots of examples of this. Now we want to look at what is this essentially opposite of the product rule. It's integration by parts. If you remember the product rule, you do u multiplied by dv dx plus v multiplied by du by dx, but if you can just multiply, if you can just integrate one of them, you can use our addition rule for integration to reverse this process. So this, I'm just going to give you the formula. That's just equal to uv minus the integral of v du by dx dx. Perhaps I'll do a video showing where this comes from, and of course there'll be all these topics, more examples, but for this brief summary, as I say, I'm assuming you've seen all these just to remind you of the techniques. This will do, and we'll get on to H6. So H6 is being able to integrate using partial fractions that are linear in the denominator. Well, this isn't linear, but I assume this is what it means because I remember doing the exams on these specifications and you would have to solve ones of these. But anyway, linear in the sense that each one of these is linear. So when you do the partial fractions, they'll all have a linear denominator, but I can, confuse it. It's not linear. So what you do is you essentially write this in the form a, and that's a capital A, over ax plus b plus b over cx plus d, and you integrate that, and that often makes it easier because you can start to use like the log bottom rule and all stuff like that, which is, for those of you who don't know that, if you've got a let's get this the right way around. I believe it's f dash is on top, you got f of x with respect to x, that's equal to ln by the modulus of f of x. Alright, so you can see how this might how you get into that form, and the way you do this is you set f of x for ax plus b at cx plus d, and you set this identical to a of x plus b plus b over cx plus d. Right, And now, because this is an identity, that implies true for all x. So what you do is you just substitute in values of x, and then you can essentially you can either come up with simultaneous equations, or you can choose values that, say I choose x equal to minus b of, alright, that is going to get rid of, in this case it will get rid of the b, because what you do is you multiply up by ax plus b plus cx plus d. That will give you f of x is equal to a multiplied by cx plus d plus b multiplied by ax plus b. You can see how you can solve that. So you can either substitute in things like this, or you can do something called comparing coefficients. As I say, we'll see. I'll do I think I already have done one on partial fractions, but I'll do an updated video as well. And we'll move on to H7. Right, so now we get on to differential equations, which is to do with integration. So you only have to deal with ones that are separable, which means you got a function of x, a function of y, and you can separate them. So what we're going to do is, onto one side, dy, that's equal to f of x dx. That's not really, doesn't technically make sense. We're going to add an integration sign to both sides, and then when you integrate it, you just want to remember to add a constant of integration to only one of the sides of the equation, right? But just make sure you put on at least one. It can be on either side. And then sometimes you'll be given starting values, so it might be that y of 1 is equal to 3. Alright, so that means y is equal to 3 when x is equal to 1, because if it's dy by dx, then a function of x, and that's not the same f of x. I shouldn't have used f. We'll use a capital F, right? That's what we're trying to solve for. So we want to get it to here, and then this is going to give us some function in terms of y. This is going to give us an x. We can rearrange it in the form y equals f of x. Use our initial conditions to find solutions. And now, this is pretty similar. H8 is just being able to apply these to real world situations. So whether that's a population where you've got dy by dx might be, or you might have, say, dr by dt, and r is the number of rabbits each time. So this is how the rate of increase of rabbits changes over time. But so you want to find how many rabbits there are as a function of time. Okay, so you'd want to find r in terms of t, and then you might say at time t equals 0, r is equal to 100,000. And you want to see, and then you might be able to identify limitations. That's another thing you should be able to do. Well, once r hits 0, perhaps, in a model, if the model's decreasing, then after that the model's not going to be suitable anymore. So that might be a limitation, because once the number of rabbits starts becoming negative, well, that's not applicable to a real world situation. Or say you want to model tree growth. Right. Well, any model that predicts negative tree growth, again, well, trees don't grow backwards. It doesn't make any sense. Right? So it's just being aware of these limitations, and using tools like this can be very, very helpful in modeling the real world. It's just you don't rely solely on the numbers. You want to use a balance of your intuition and your logic and what you know from the real world amongst these mathematical tools to help you find specifics and see things and patterns that you wouldn't perhaps be able to see. So that's it for this brief summary of all the integration stuff. I will go into all of this in much more detail. You know, this was just if you got an exam coming up tomorrow, or you just wanted an intro, or a little summary of what you've been revising over the last few months. So I hope you enjoyed. Please like and subscribe. If you haven't seen already, I did a similar video to this on differentiation, and I'll do it on all topics. And as I say, if you want different specifications, then be sure to comment that below. Any requests for videos? But for now, that's it. Thank you very much for watching, and I hope to see you in the next one.